Hello students, this is our second lecture in the fourth module. This will be the penultimate lecture of the course. So in the previous lecture, we have started looking at some of the program optimizations that we can do to improve the performance. So there were code motion, reduction in strength. In that we have seen two aspects: to replace complex operations with simple operations, depends on the way the hardware is built. The second was to share common expressions among multiple instructions or multiple lines of the code and calculate them once, reuse many times. And the third point was to remove any unnecessary memory references and try to keep the data in the registers and reuse the data as much as possible. In the last lecture, we also saw that the modern compilers have a couple of limitations or performance blockers. One was they are very conservative with pointers, specifically because of memory aliasing. The other is the way they handle procedures or function calls. They usually treat the function call as a black box and don't try to optimize the code across multiple function calls. So in that regard, the three optimizations that we have seen will be a little more helpful to optimize the code. Now in this lecture, we are going to look at a couple of things that the compiler does to exploit the underlying pipelined way of execution. We have already touched upon one of these, so you will realize that as we go. Pipelining basically exploits the parallelism in instruction execution. It overlaps execution of different instructions in different stages, so it's called uh, instruction level parallelism. Pipelining is set to exploit ILP. The stalls in the pipeline are predominantly due to any sort of dependencies, either data or control dependency, which might eventually result in hazards and stalls or maybe flushing the pipeline. Now, to address these dependencies, one of the thing which we have touched upon in second module in the pipelining topic was to space out the dependent instructions so that at the pipeline we need not stall. So during the discussion, we explored a possibility of reordering the instructions during the compilation time, and that's what we are going to look at right now a little more in detail with an example. So let's consider a simple for loop which will iterate 1000 times. All it does is take an element of an array, add a scalar to it and write it back to the same element. And let's assume that the address of the last element of the array is available in x4 register. X1 has 999 and the value 999, which is the starting value, and x6 as the value of the scalar. And let's assume that the word size is 32 bits or 4 bytes. Also, for simplicity in explanation, let's assume that there is data forwarding but nothing specific with related to control instructions. That means there is no branch prediction, or we are not trying to move the branches from try to resolve the branches from the execute stage or and do that in the decode stage. The simple regular branch flow wherein we are going to resolve the branch in the execute stage and decide the next PC value in that stage. So let's look at the RISC-V code. So this is how it would look. I have just introduced the first instruction, add x3, x4, x0, just to take a copy of x4, that's all. The main loop is between the dotted lines. Let us label the instructions. So I1, I2, I3, I4, I5, I6 are the loop that we are currently concerned about. I7, I8 are some fall through code, not of primary concern right now. Let's see how this code executes, and let's try to understand where the possibility of improvement is there. Before that, let's quickly look at the possibility of stalls or need to flush the pipeline. There will be one stall between I1 and I2 because of the dependency on X5, which will be available only at the end of memory stage, and we would need it at the beginning of execute stage for I2. So we need to wait for one cycle. So that's a stall. There is no stall required between I2, I3, I3, I4, I4, I5, I5, I6. But I6 every time, which is a branch instruction, because we are resolving the branch in execute stage, if we see that the branch is taken, we need to flush the pipeline for 2 cycles. So let's look at the timeline here. Let's say the clock cycles are C0, C1, C2, C3, so forth. And let's look at the execution of the 6 instructions of the loop: I1, I2, I3, I4, I5 and I6. So in C0, I1 will be fetched. In C1, it will move to decode and I2 will be fetched. In C2, I1 moves to execute stage, I2 will move to decode and I3 will be fetched. In C3, I1 will access the memory to fetch the data. Because there is a dependency, we introduce a stall. So I2 and I3 do not make any progress in C3. In the next cycle, C4, I1 moves to write back stage and now I2 progresses to execute stage and I3 progresses to decode, and we fetch a new instruction I4. In C5, I2 moves to memory, I3 moves to execute, I4 moves to decode, and we fetch I5. So in C6, I2 will be in write back stage, I3 will be in memory stage, I4 will be in execute stage, I5 will be in decode, and we fetch I6. So this was the first cycle wherein we were successfully able to engage all the stages in the pipeline. Similarly, in C7, what happens is we fetch the fall through code I7 because we don't yet know the path the branch would take. Similarly, in C8, wherein we are actually resolving the branch and we don't know the direction yet, we fetch the instruction I8. At the end of the cycle, we would know the branch direction. So here, excuse me, I'm sorry, we realize that I7, I8 are not the required instructions or the instructions in the required path. So we flush them, and in the very next cycle, we start fetching from the target. In the same cycle, I5 progresses to write back stage, I6 to memory stage, and we fetch I1, which was the target of the branch instruction. So in C10, I6 is in the write back stage and we fetch I2. So if you look at one iteration of the loop, it would take C0 to C10 cycles. So we need 11 cycles for one iteration of the loop. That means to do addition of one element of the array, we would need 11 cycles. Now if we try to visualize what happens across two iterations, we would need 19 cycles because there is an overlap of C9 and C10 here between the first iteration and the second iteration. So instead of 22, we have 19 cycles. Now, the main issue we are facing here, or it's an issue because we are not able to fully utilize the pipelining hardware. It was because of the data dependence between I1 and I2 and the need to flush the pipeline whenever we are to change the direction of the PC. Now let's see what can be done there. The very first thing is to look for possible safe instruction and replace or place it between I1 and I2. I have picked the ADDI x1 x1 -1 instruction to be safe and I have placed it between the load and the add instruction. So this is how our loop would look like. Now I have just labeled them like earlier: I1, I2, I3, I4, I5 and I6. And if you look at the stalls or the flushing of the pipeline that would be needed, we do not have any stalls between I1 and I2 because there is no data dependence. Similarly, I2, I3, I4, I3, I4, I4, I5, I5 and I6, and after I6 we have 2 cycles to flush the pipeline. So if you look at the cycle by cycle execution like earlier, so here we have the 6 instructions. We would fetch the first one in C0, fetch second one in C1, third instruction in C2, fourth instruction in C3, fifth instruction in C4, and sixth instruction in C5. Because of the instruction reordering, earlier we had a stall in C5. Now because of the reordering, we do not have a stall and we have actually attained the maximum performance of this pipeline in C4 itself. We were able to engage all the hardware. In C6, we would continue with fetch of I7. In C7, we will fetch I8, and at the end of C7, we will now know the branch direction and flush the pipeline and start fetching I1 in C8. And in C9, we fetch I2. This is I2 for the second iteration of the loop. Now if you look at the timeline for one iteration, we would need only 10 cycles. We have saved the 1 cycle stall just by reordering the instructions. And for 2 iterations, it would be 17 cycles. This way of reordering the instructions is called static pipeline scheduling. It will be done by the compiler during the compilation time. It will look for possible dependencies and space out the instructions with safe instructions so that the dependency will not eventually result in any stall. Now the feasibility of the compiler for moving or reordering the instruction will depend on the available ILP in the program. Here ILP is the aspect of instructions being independent of each other. When we say the instructions are, every instruction in the program is dependent on the one previous to it or to the instruction next to it, we would say ILP is very low, because the possibility of executing them in parallel will be less, because we need to introduce stalls every now and then. So if we have safe instructions to move around, then reordering will be easier for the compiler. Also, the latency of the functional units will determine the number of stalls we need to introduce for any dependency. Now, in the previous example, we have assumed that all the operations, let's say add or subtract, everything would happen in one cycle. Now, we have studied that for many instructions, we would need multiple cycles. For example, floating point multiplication, addition, division, or even integer multiplication or division will take multiple cycles. So in that case, the compiler needs to find so many instructions, safe instructions to place between the producer and consumer. It might not always find so many instructions. In that case, we will eventually end up with a stall. So during the compilation time, the compiler identifies all the possible stalls based on the dependencies and based on the operation latency, and tries to fill them with safe instructions. Continuing the discussion, in the earlier example, in an iteration, the actual work was done by only 4 instructions. We had 6 instructions in the loop. Only 4 of them were doing what we actually wanted. We wanted to load that array element, add it, store it back, and move the address to the next element so that in the next iteration we can load it. So the other 2 instructions were introduced to realize the loop. So which were the loop iterator, the increment or decrement, and the actual branch instruction. And because of these instructions which are not directly useful to us, there can be some stalls or we might need to flush the pipeline. So this is called loop overhead. In order to handle loop overhead or minimize its influence on overall execution time, we have a simple technique used by the compiler called loop unrolling. What it does is it tries to increase the number of useful instructions per iteration so that the loop overhead gets amortized across multiple iterations. What basically loop unrolling does is it replicates the loop body multiple times and accordingly adjusts the termination code. Let's look at the previous example and let's try to unroll the loop 2 times. So here is the code unrolled twice. I have labeled the instructions I1 to I10. I1, I2, I3, I4 are the instructions for the first iteration. I5, I6, I7, I8 are same as the previous 4, just with there is no change here. We have just copy pasted the same instructions. This way we have actually unrolled the loop twice. So this is the first in one single iteration we are handling the first element with the first four instructions and the second element with the next four instructions, and we need to change the loop iterator. Now instead of the loop running 1000 times, we would like it to run only for 500 times. So we are subtracting the iterator element by 2 every time. Now if you look at the stalls or flush for this sequence of instructions, we would need a stall between I1 and I2 because there is a producer consumer dependency. There is no such dependency between I2 I3 or I3 I4 or I4 I5. Again, we have a dependency between I5 I6, no such dependency among any other instructions. But for I10, which is the branch instruction, we would still need to flush the pipeline for 2 cycles, or the previous 2 stages would need to be flushed. So if we look at the timeline, just like the previous example, we would need 15 cycles for one iteration of the loop with such a sequence. But we already know that there's a possibility of reordering. So if I move, let's say I9 somewhere between I5 or I6 or I1 or I2, I can reduce one stall. So the iteration would take 14 cycles, and per iteration we are actually handling 2 elements of the array. So effectively we need 7 cycles per element. Earlier it was nearly 10 cycles. So we have saved 3 cycles per element of an array, and we had 1000 such elements. So effectively we have saved 300 cycles or 3000 cycles. So which is a huge improvement. Now the loop overhead, which was 2 instructions earlier, is still there, and the associated stall or flush is also there. We are not reducing the loop overhead, but now it got amortized because we are handling 2 elements per iteration. What can we do better? When we unroll the loop earlier, we have reused the same registers. So for example, we have used I5, I4, I6 in for the first element and the second element. So that has limited the reordering possibility for the compiler. Now if we use different registers, then the unnecessary dependencies would be removed, and we would be able to reorder the instructions to reduce any more stalls or any other stalls. Now I have changed the register I have used for the second element in the iteration from x5 to x15. All the green ones are belonging to the second element. I have loaded the element ai-1 into x15. I have added it to x15 and storing it back with the same register x15. Earlier we have used x5. Now I have also reordered. I have moved, this was earlier I5, I6, I7. Now we have made it I2, I4 and I6. So what are the key observations here? We have reduced one additional instruction when compared to the previous example or previous blindly unrolled loop, because we were decrementing x4 twice earlier, but now we are decrementing it only once. So we have reduced one instruction. Also we were able to reorder a little further and reduce the stall between I1 and I2 earlier. Now we do not have any stalls from I1 to I9, but after I9 we need to flush the pipeline for 2 cycles because of the control hazard. Now if we have effectively reduced one more stall, so we need 13 cycles per iteration of the loop in which we are handling 2 elements. It means the effective number of cycles per element has now come to 6.5 cycles. We have brought it down from 10. If you want to handle branches, and let's say we have the delayed branching concept in the hardware and the compiler is aware of it, and let's say there was one branch delay slot, what we would do is we would pick some independent instruction and or independent or safe instruction and place it after I9, which we expect to be executed no matter what. So in that way we would further reduce the stalls required for the control hazard. So in loop unrolling, if we simply replicate the instructions, then because same registers are being reused, it might create some additional dependencies and reduce the scope for reorder. So to get the best out of loop unrolling, we would need to use different registers. And loop unrolling is one of the first steps the compiler would explore, so that all the further steps in compilation would use such optimized sequence of instructions and work further to reduce the computation or overall time. Now, in the previous example, we have considered a loop which would iterate 1000 times, and we have unrolled it twice. So we have now reduced the number of loop iterations to 500. But what if the number of times the loop would iterate is not a multiple of the number of times you want to unroll? For example, if we wanted to unroll the previous loop by 3 times, then we would cover only 999 iterations of the 1000 iterations. So we have to handle either the first element or the last element separately. So this is a side effect of loop unrolling. We can't blindly go ahead with it, and we need to write additional code for such corner cases. There is one more difficulty that we might face at the compile time. What if we do not know the upper bound of the loop? Earlier we have considered, we know that the loop was iterating 1000 times because 999 number was present in the for loop statement itself. But what if there was no such number there but some variable? Then how do we decide how many times we have to unroll? Or how does the compiler decide? Is based on another concept called strip mining. So let's say the loop has a variable n, which is the upper bound, and we do not know n at the compilation time because n depends on some other prior calculations, and those will be determined only at the runtime. So what strip mining does is it makes k copies of the loop. In the process, it makes 2 pairs of loop. The first loop executes for n mod k times, and the second loop executes for the n by k times, the remainder of it. So let's look at the example here, and the basic condition for the strip mining to work is to pick a number k which is less than n. So again, the compiler needs to do some extra processing to find out what would be the suitable k. Let's consider a simple for loop here. It's iterating n times, but we do not know, or n minus 1 times here, but we do not know what n would be. We would, if we would do something like the code in the second box, if we know that n is a multiple of q, what we would do is the outer loop will have can have a variable k, and it will make a stride of q every time. But within that we have an inner loop which will process each of those k elements or q elements, and then I increments by to q plus uh, q times, and for the next q elements the inner loop comes into the picture. Now we can look for possible loop unrolling of this inner loop because we know the value of q. Or how does the how does the compiler estimate the value of q is by looking at the code. Here is an example. Let's say we have a for loop. Inside that we have a set of statements like this. If I mod 64 is equivalent to 0, only then we would execute f of I. G of I will be executed for all the loop iterations, and h of I will be executed similar to f of I whenever I mod 64 is equivalent to 0. By looking at this code, the compiler makes an estimate that if I want to unroll, 64 is likely a good number. So it blindly, if it wants to do, it will unroll the loop 64 times, meaning g of I will be repeated 64 times, g of I to g of I plus 63. So this is what unrolling would mean here. But with strip mining, what we have is we have the outer loop which makes a jump of 64, and for each of those outer loop iterations f of j and h of j would be executed. But for each of the 64 jumps, within each jump we would execute g of I 64 times with the inner for loop. Now this inner for loop can be unrolled any number of times. It need not be blindly 64. This is delta step before the final loop unrolling. So in summary, of the instruction reorder and loop unrolling that we have discussed today, to obtain an optimized code, we would first look for the possibility of unrolling the loop. It might not be so straightforward because many a times the loop iterations themselves might be dependent. In such cases, unrolling the loop can be a little more tricky because the dependencies need to be handled carefully so that the correctness is preserved. To better make use of the unrolled loop, we would need to use different registers to avoid any name dependencies, unnecessary ones, and reorder them. And we would eliminate any extra test or branch instructions if that possible, and adjust the termination condition and the overall iteration code itself. Also, we can look for the load and store instructions within the unrolled loop, and if they are independent, they can be used as safe instructions and can be introduced between any producer consumer instructions. without creating any additional dependencies or without resulting in any incorrect final value. So we should reorder the code only when we are very sure that the reordered instructions when executed will still give the correct output. Some limitations of loop unrolling. We would see a decrease in the amount of loop overhead that gets amortized with each unroll. For example, when we unroll the loop 4 times and next when we unroll the loop 8 times, it would be highly unlikely that we would see an performance improvement which is twice of what would have happened if the loop was unrolled 4 times. As we increase the number of times we unroll the loop, we would get diminishing returns. So at some point we need to draw a line saying that even though, let's say, the loop is for 1 million times, beyond unrolling 10 times I won't be able to find any extra improvement. So we would unroll it only 10 times. So do remember that the compiler needs to do such an estimation and take a decision at the compilation time itself. Because of unrolling, the actual code size increases, which can result in additional instruction cache misses, because instruction cache, which is the first level of cache, is typically small because it needs to match with the speed of the pipeline. But if the actual code size is increasing, then we might end up with additional instruction cache misses which we would not have seen if the loop was not unrolled. So this is something we need to this is a side effect that can happen with loop unrolling. Also, across multiple unrolled uh, loop iterations, if we are using different registers, we found that the reordering would be easier, or there is more scope of reordering, but the number of registers are limited. So if you want to use new registers every time we unroll the loop, this would create extra register pressure, or it might even result in register spilling also. This particular issue will aggravate in multi-issue processor. We have not discussed multi-issue process here, but to quickly explain, there will be many more instructions in flight in a multi-issue processor. So many more registers would be used up by the in-flight instructions. So to get any new registers or to allot them to the newly unrolled loop, it will create even more pressure. From the compiler end, the modern compilers are complex enough that they have many more sophisticated transformations which might actually overshadow the effectiveness of loop unrolling itself. Loop unrolling was one of the basic techniques people have explored, and over the years there were many other techniques, not with the hardware in view, something at the algorithmic level or at the high level language code dependency level, or looking for dead codes or looking for the basic blocks and optimizing them further. There are uh, tens of optimizations that the compilers do. You would go come across them in the actual compiler course. With all those, the loop unrolling effect might get nullified. So there is a very limited scope for loop unrolling as such. But I have decided to touch upon it because to gauge the importance of loop unrolling, we need to actually have an understanding of the underlying hardware, how the instructions are getting executed, where would the possible dependency be, and how to reorder the instructions, and how to how many times we can unroll the loop so that overall stalls would get minimized. So with that, here is a small hands-on experiment for you to try out. Take any simple loop, it can be the one which we have discussed in this class, and write the RISC-V code. As you already know, there are multiple ways to multiple assembly codes for the same C code. So whatever I have discussed was what I came up the very first time I thought about it. It might not be optimized at all. So you can, if you have some optimized code, you write it, do the task 1, task 2, task 3 in that order, reorder the instructions in the first task to reduce the stalls. As task 2, unroll it 2 or 3 times, and now look for reordering the instructions. As task 3, unroll the loop and use different registers and try to reorder. After completing each task, run the code on the RISC-V simulator that you have developed and see how many instructions have been executed, how many cycles they have taken, and of them how many stalls are there. We would expect that the number of stalls for task 3 would be lesser than task 2, and which would in turn be less than task 1. So I hope you will be able to make the observation yourself. This would give a good intuition on why the static scheduling and group unrolling would be helpful, or how they would be helpful. The more the dependencies in the original loop, the better the effect would be with reordering and loop unrolling. So with that, I will conclude this lecture. The next lecture would be the last lecture of the course, wherein we are going to look at program optimizations with the underlying memory hierarchy in view. It means we would look at the program and try to increase its locality, because the entire memory hierarchy is based on locality. So with that, I'll pause this lecture. Thank you.